So let's see what active devices are. We're going to have some active audio filters. I bet they're made with operational amplifiers. Maybe. Some of the characteristics and circuit design and operational amplifiers. So, an operational amplifier is an analog device. It's a extremely high gain differential amplifier. It has very high input impedance and low output impedance. It's kind of a little building block. You can do filters with them, make active low pass, high pass, band pass. You can make an active inductor or capacitor with them. And you can make a 1 farad capacitor with an op amp. Just all kinds of fun things. So what is an operational amplifier? Yep.
Alpha, yep.
What's the typical input impedance of an op amp?
Delta,
Very high. What's the typical output impedance of an op amp?
alpha.
Very low. We've
seen this before.
We have?
That
Well, it's not quite the same as the filter. This is gain bandwidth product. Well, same kind of effect. Right. An operational amplifier, well, most amplifiers have a gain bandwidth product, which means if you multiply the gain of the amplifier times the maximum frequency it can operate at, the 3 dB down point, that's its gain bandwidth product. So if you try to get higher gain, you have a less frequency range, or if you try to get a higher frequency, you have to reduce the gain because you can't exceed the gain bandwidth product. Does that make sense?
I think not. Simply, the first bullet there, that's a unity gain amplifier. If it has a gain of 1. Right?
With a gain of, well, it can be. It means that that amplifier at a gain of 1 will operate up to that frequency. Okay?
That's the bandwidth product.
Right. So if I multiply that frequency times the gain, that's the gain bandwidth product. It's the same number because it was 1, right?
Okay.
1 times the frequency. If I change the gain to 10, what's the maximum frequency? 1/10 of the gain bandwidth product.
Gain directly for the band.
Yeah. It's the product of the two that determines this limit, and that's that curve you see. Now it has some upper limit as far as gain physically. I mean, you can only go so far. But within that operating range, you see at lower gain, you get a higher frequency because you're out here on this part of the curve. The slope is the gain bandwidth product. So unity gain is down here, and that's the highest frequency. So it looks like the low pass filter, but it's not.
Yeah,
How does the gain of an ideal operational amplifier vary with frequency? Kind of a trick question.
I do.
delta,
Well.
does not vary.
You think? You think?
No, wait a minute, I don't think, and. Ideal.
What varied with frequency? Okay.
So it's gotta be A and B.
Yeah, but the way it's worded. So how does the gain vary? Okay. The gain's part of the bandwidth product, gain bandwidth product.
Doesn't care
So
about
the gain is
frequency,
limited by frequency.
but it does
As
not.
the frequency changes, does it vary the gain?
No,
It's on that line. Yeah, but it's that line.
All right, I'm down here at a gain of 5. Say that's what that line is. This, so as I go along this line, I'm changing frequency. The gain hasn't changed. Right?
Right.
I don't have a problem till I get up to the line and then I start losing gain. So at that point, the gain changes with frequency, but not in the operating range. It's not a very good worded question.
Well, let's go back. The question though says ideal, which means you never have implementation.
Well, okay, that's true. That's true. The gain bandwidth product is infinity, right?
Well, that's like that green ball. Now, ideal, that was working along the slope.
Okay.
Yeah, we forget the slope on this question. Yeah, it's a trick. It is kind of a weird word, and they do that. Yeah.
No, I don't know that they do. I think they just come up with some dumb worded question. What's the gain bandwidth of an operational amplifier? Now you ought to be good at this one by now.
Should be, but I'm fine.
1. Bravo,
Oh. Sorry.
All that time?
I think we work on it together long.
The gain of 1. Essentially the maximum gain that you can get at that frequency.
It does say open loop. Yeah, it does. Yeah, that's what could be. See that. Yeah, okay, go back. Oh, I put, where's the open loop? Open loop gain.
Open loop gain equals 1.
Oh, I'm looking on the diagram there, gee
Oh.
whiz.
yeah, read.
Yeah, because I took that right off of the question. Or the answer, I should say. You'll remember that one.
Probably. I don't.
All right, we have another issue, input offset voltage. Because even though it's a differential amplifier, In the real world, those two inputs may not be exactly balanced. So if I have the same signal on both of them being a differential amplifier, a plus and minus, I should have zero out, but I may not. Okay, because I could have an input offset. So whatever that offset is would give me an output. So I may have to compensate for that input voltage to get the output to zero. It's going to be pretty small. But then again, you could have a gain of 10,000 on that operational amplifier. You don't need to have to calculate it. What is meant by the term op amp input offset voltage?
Charlie. Charlie.
It's the correction voltage you need to get it output to zero. You have to compensate for whatever that offset is on the input.
I understand it, I just didn't get the word.
Okay, here's a whole selection of operational amplifier circuits where you can have differentiators and integrators and just a straight differential amplifier, a summing amplifier, voltage follower, kind of like an emitter follower type, where it's a buffer. And then a comparator. Most of the time you're going to have an inverting amplifier. Sometimes you see non-inverting. It's harder to calculate. You don't have to do that. You will have to do these. There will be math involved. Division. So calculating the gain of an output
Excuse me a
voltage.
second, Bob. I didn't see it mentioned, but sometimes the FET input op amp is very important because of the input leakage current.
Probably true.
Definitely true, but I didn't see the FET input different type mentioned.
Because it's not part of the exam questions,
Okay,
at least not yet. Now you could submit that question.
Don't you dare.
Okay, so to calculate the gain of an inverting op amp, it's fairly simple where you take the feedback resistor and divide it by the input resistance. And that ratio gives you the gain of that amplifier.
Oh.
Down here. Yeah. Well, that's for voltage out. The gain is just the ratio of those two resistors.
Yeah, oh.
Okay, ready for question? What magnitude of voltage gain can be expected from this circuit when R1 is 10 ohms and RF feedback resistor is 470 ohms?
C, Charlie.
Charlie sounds good.
Pretty hard math.
Yeah, you need your calculator, right?
Yes.
What absolute voltage gain can be expected from the circuit in figure E7 3 when R1 is 1800 and RF is 6800? Ooh, you might need your calculator for that one. So you got 1.8K and 68K.
37.77777 or 38.
We'll round up.
Well, it's obviously not alpha or bravo, right?
Delta's the only thing conceivable. It's 37.7.
So if I rounded them to 2K and 70K, that's
Oh. Welcome to the world. Very sensitive.
yeah, that-
Okay. You know, because,
what'd you get?
38.
Okay. Okay, what absolute voltage gain can be expected when I have 3,300 ohms and 47 kiloohms? Good chance you get one of these because there's a lot of them.
B. Bravo.
Did you get that one?
they're trying to pick me by saying regular ohms and kilo ohms, so if you don't forget kilo ohm, you get one of those interesting. The same K.
Yeah, they
47 by 33.
do that to see if you remember the conversions.
Yeah. Trying to. Yeah, oh, I could never, I'm colorblind, I could never do that. But it was a full multimeter one.
Bob, how long are we going today?
Well, we got one more session to go through. It shouldn't be too long, but we're going way over. Okay. We got another one here. R1 is 1,000 and RF is 10,000. Ooh,
That's
really high math. And the input voltage is 0.23 volts.
Baker. B.
Gonna make you think now.
You ready?
Delta.
This is kind of a tricky one.
I had the 2.3.
Yeah, but you forgot it was inverting. It's an inverting amplifier. So if you have plus,
Were the others? Negative.
Yeah, we can carry about those questions.
I don't think they asked for the output voltage, did they?
Oh,
They just want
they
gain.
want a gain.
Right.
Okay.
You know, that's an inverted.
Yeah, that's a trick one.
Yeah, it's fine, gain.
Because you figure, well, the gain times 2.3 obviously is 2.3 volts. Okay, we can make active filters. At least in the audio range. I guess most of the op amps I've dealt with don't have very good high frequency capability. Or not a very high, well, shouldn't say not a very high gain bandwidth product because it can have a lot of gain, but. So if you add some capacitors in the feedback circuit, you can make it, or in the input circuit, you can make it a high pass or low pass filter. One of the issues, because they're very high gain devices, particularly in circuit layout, where you've got some stray capacitance and stuff like that, you can get oscillations and feedback. So one of the things is you may have to restrict the gain or the Q of the circuit. So if we have our basic circuit and now we add a capacitor to the feedback resistor, what happens?
Filter.
Is it going to make it a high pass or a low pass?
Low pass.
What's the capacitor going to do as the frequency increases? Okay, so it's effectively going to reduce the R2, right? So the higher the frequency, the less resistance or in that ratio. So in this case, if we added that feedback resistor, is it Alpha Bravo Charlie or Delta? Because at low frequency, the capacitor doesn't have any effect. So it's still the same gain. But as the frequency goes up, the gain starts dropping, which is what a low pass filter does. How can unwanted ringing and audio instability be prevented in an operational amplifier for audio? Restrict gain and Q. Okay, let's move along. Get this last one out of the way.